Presented by Caltech.
Good evening. My name is Tom Sofer, and I'm the chairman of the Division of Physics, Math, and Astronomy here at Caltech. Before I introduce tonight's speaker, I want to tell you about the last Watson lecture of this academic year. This will be in 2 weeks on May 20th. Professor Catherine Faber will speak on Watching Paint Dry and Colors Fade, the intersection of art and science. So now it's my pleasure to introduce tonight's speaker, Jamie Bach, Professor of Physics and Senior Research Scientist at JPL. Jamie received his undergraduate education at Duke University and his PhD in physics in 1994 at the University of California, Berkeley. Jamie is one of the world's leaders in the quest to detect the first instant in the universe that we live in. This instant is referred to as the inflationary epoch. This quest, to put it in terms of the experimental approach to detect and map the Curl mode polarization in the cosmic microwave background radiation, is one of the great scientific endeavors of our time. It is a very high-risk experiment, but its payoff will be huge. It has therefore attracted the very best people in physics, and Jamie clearly stands out within this illustrious crowd. Jamie came to Caltech and JPL in 1994 with Andrew Lang. He was, as well as being a research scientist at JPL, he's been a visiting associate at Caltech and then a senior faculty associate, and he was appointed as a professor of physics on campus 3 years ago. Jamie built at JPL and on campus the world's premier laboratory for constructing the sensors that actually detect the radiation that reaches the Earth from 380,000 years after the Big Bang. These detectors are the heart of microwave background experiments. His sensors have played crucial roles in experiments on the ground, from balloons, and in space. Because of his leadership in the science and the technology, Jamie has been the principal investigator of experiments on the Planck and Herschel space missions, on balloon experiments that have flown from Antarctica for well over a decade, and on ground-based experiments Bicep, Bicep 2, Keck-Array, and Bicep 3 that operate from the South Pole. After his talk, Jamie will take questions from the audience. And so with that, let me join me in welcoming for tonight Jamie Bach, who will tell us about the quest to find the first instant of time in his talk, Searching for Vibrations from the Big Bang. Jamie Bach.
Thank you very much, Tom. 15 years ago, our group began a quest, a single-minded pursuit of a polarization signal in the cosmic microwave background coming from an epoch of time called the period of inflation, associated with the very birth of our universe. The signal would be produced by vibrations from inflation, a background of gravitational wave radiation. Well, we started out this quest modestly with a few ideas, but in those 15 years, we've really made a lot of progress. We've invented new technologies and new methods that are now giving us beautiful measurements from the ground, from high-altitude balloons, and from outer space. The talk I'm going to describe tonight is really still a hunt in progress, and I would say it's a hunt that's in its most exciting phase. We finally reached the sensitivities we need to push into new territory to test inflation. And in the next few years, our program, and combined with other observatories, will test what some would say are the first and simplest models of inflation it will be in that regime. So I think that's a truly exciting notion, and I hope to share some of that excitement with you tonight. I like to show this slide because it's a woodcut from the 1800s, but it really shows the spirit of what we're trying to do. Here, our intrepid explorer is trying to see behind the current stars to see if there's a universe behind that. And it raises the question, how far can we see in the universe? Is there something behind the universe we see with our eyes? Well, there's a few details missing from this picture. You may notice them. One of them is there's no galaxy. So in the 1800s, we didn't really understand how enormously vast our universe was. The other detail that's missing here is the speed of light. Now, they knew about the speed of light, of course, and so when our observer looks back at this tree, he's seeing the tree nanoseconds before the light was emitted. And if you look back at the moon, we're seeing it a fraction of a second in the past. The sun's 8 minutes in the past. And the nearest stars are a few years in the past. But because the scales of the universe are so vast, this time effect is large. And so when we look at distant galaxies, we're seeing those galaxies as they were billions of years ago in the past. But can we see a time before there were galaxies? And the answer to that is yes, we can. The universe is expanding. And so when we look at nearby galaxies, we see them further and further back in time. But we're also seeing the universe when it was smaller and hotter and denser. And the further we look back, the smaller and hotter and denser it gets. We reach a time eventually where the universe is so hot that the hydrogen atoms ionize. What that means is they are no longer atoms, they're free protons and electrons. And those free electrons strongly scatter light. Before this time, and so that period of time here is shown on this view graph at about 380,000 years after the Big Bang. And the present age of the universe is 13.8 billion years. Before this time, the universe was so hot that the electrons strongly scatter the light. And after this time, when neutral hydrogens formed, the universe becomes very transparent. And so to good approximation, the photons we see at the surface don't interact. They free stream all the way to our eyes. So when we look at the cosmic microwave background, we are seeing the oldest photons in the universe. We're seeing a time before galaxies when the universe was 1,000 times smaller, hotter, and denser than it is today. To make a bit of an analogy here, if the current universe were a middle-aged adult, the time here at the recombination corresponds to about 8 minutes after conception. Okay, so we're seeing a much different picture of the universe then, much as we would see a much different picture of two cells splitting after conception with a human. However, this period of time is also something of a curtain. We can't see past it in light. And so if we want to understand what happened earlier in the universe, we have to look in other means. We can't go further back with light. Or perhaps we can study in detail the properties of the microwave background and infer what had happened at those earlier times. So you may know that thermal emission has a characteristic spectrum. So when we look in the optical, for example, with our eyes, we can see objects that are very hot, like the sun. It's about a temperature of 6,000 Kelvin, or a candle. As we look at cooler objects like people or dry ice, the peak of the radiation moves to longer wavelengths. The cosmic microwave background is currently at a temperature of 2.7255 Kelvin. And based on the number of digits, you can see perhaps that this is a very well measured spectrum. But at the time when hydrogen was ionized, the universe was filled with a glow that was much hotter. In fact, it was a temperature of about 3,000 Kelvin, light that you could see with your eyes. It's like the temperature of a low-mass star. And what happened is the enormous expansion of the universe a factor of 1,000, stretch that radiation out from its characteristic temperature of 3,000 Kelvin all the way down here to 2.7255 Kelvin. So when we study the microwave background, this radiation peaks here out in the millimeter wave. And so that's where we do our measurements. So just to catch you up to speed here on cosmology circa 1980, we know the universe is expanding. We also know when we look at nearby galaxies, they're all receding away from us. Edwin Hubble discovered this on Mount Wilson here in Pasadena in the 1920s. It was once filled with radiation, similar to the temperature of the sun, and now we can still see the glow today in the form of the cosmic microwave background. And these three things really form the pillar of the fact that the universe had a beginning, and that beginning was a hot beginning. But our story doesn't end here. If I make a map of the sky at optical wavelengths, this is what I get. This was made by a project called 2MASS, which mapped the whole sky. It's just like a map of the Earth, except instead of looking down, I'm looking up. And I've arranged the coordinates. So this isn't the equator of the Earth, it's the equator of the galaxy. Okay, and this looks kind of familiar. You can see stars and galaxies. You're looking at a bit longer wavelengths than optical, as it turns out, so you can see the galaxy looks a bit different. Here's the Large Magellanic Clouds. So that's what a picture of the sky looks like at optical wavelengths. What does the sky look like at millimeter wavelengths? This is what the sky looks like at millimeter wavelengths. This is actually real data. I'm not making this up. This is data that comes to us from a satellite called COBE. And what you can see is that the temperature of the microwave background is incredibly uniform. Everywhere I look on the sky, the temperature is the same to 10 parts per million at this angular size. And this may not keep you up at night, but in the 1980s, this was a real problem. Theoretical cosmologists just couldn't understand this. And the reason is that when we look back at the microwave background, we're seeing a time when the universe was 380,000 years old. Light from the Big Bang could only travel 380,000 light years, okay? And the size that looks like here is about the size of my laser pointer. It's about a degree. And what that means is that every little patch here has only had time to communicate about the size of a degree. And if I look at a patch over here and a patch over here, they've never communicated, ever. And in fact, I can have light coming from this direction and this direction, and apparently that light's just getting to me now, and certainly hasn't had time to go over and talk to each other. So how can they all be at the same temperature if they've never even been in contact? Well, the answer to this puzzle, I like to make a little analogy. Imagine I'm a fly and I wake up in a room and I'm at a conference, and I'm into food and drinks and so forth, being a fly, and I notice that everyone walking around the conference is carrying a cup of coffee. And you know, they're moving around, all these cups of coffee are all over the place, I fly around, and because I'm a physicist fly, I take the temperature of the coffee, and I find that everybody's cup of coffee is this exact same temperature. And this really freaks me out. I'm thinking, like, are these people messing with me? They've all somehow synchronized the temperature of their coffee. And then I realize what the answer to this is. The answer is that there was a coffee break before I woke up. And all that coffee was in a big pot, and everyone poured their coffee out of the pot, but it was all at the same temperature. It was all connected prior to the time that I woke up. And so the answer to that in cosmology is something called the remarkable theory of inflation. And this was developed in the 80s by people like Alan Guth and others. And the basic idea is that sometime in the early universe, the entire observable universe was in a very small connected volume, okay? Much smaller than the size of an atom. And so everything in that region, light could bounce around, we could exchange information, we can all be at the same temperature. And then something happened. And that thing is called inflation. And what happened is that patch of the universe blew up to enormous scales very rapidly. It blew up, in fact, so quickly that if I have two observers talking to each other, standing next to each other, the inflation would stretch the space so fast that they would come out of communication. And you can think of this a bit like space expanding faster than the speed of light. But what it means is those regions were all connected before inflation, and then they got flung out to large distances, but they all remembered that they were at the same temperature. And then somehow inflation stopped, and the universe proceeded on its merry way. So the reason the temperature is all the same is because it was all connected prior to this time of inflation. So that seems cute, but what about like Einstein's laws? And well, it turns out that this is completely consistent with Einstein's equations. Einstein's equations say, if you give me matter and energy, I will tell space how to bend. Or in the case of the universe, you give me matter and energy, and I will tell the universe how to expand or contract. Well, you can have a weird form of matter energy. And so it's possible, for example, to have a form of matter energy that doesn't attract, doesn't cause space to slow down or decelerate. It acts as a repulsive force, okay? So that the universe would actually expand more quickly. And so that's the basic idea. You need some weird form of matter energy that acts in a repulsive way, and you can get this inflationary expansion. Now, we don't know of any kind of physics that can do this, but it's possible that at very high energies, beyond what we can probe with terrestrial particle accelerators like CERN, that such a state of matter would exist. And this expansion explains a lot. It explains, first of all, the fact that the microwave background is so uniform. And then after the universe proceeds, well, this plot has many orders of magnitude here on the x-axis and many orders of magnitude on the y-axis. And the microwave background's all the way over here, and here's the present day. So this is the screen I've been talking about. Now we want to go and learn about this very early epoch. Seems like quite a challenge. But inflation does more than that. Inflation, you might think because the size of the universe here is so small that quantum mechanics is important, and you'd be correct. Inflation takes noise from quantum mechanics prior to period of inflation and blows them up to enormous scales. And that noise turns into the structures that seed galaxies and clusters of galaxies today. So when we look on the sky and we look at enormous, majestic structures in the cosmos, those structures, according to the theory of inflation, actually began as quantum mechanical noise, which is pretty amazing. The other amazing thing is for those of you who aren't humbled by the size of the universe today, I don't know if there's anyone out there who feels they're in control of the universe, but there's sort of an ultimate Copernican revolution here. There's nothing that says that this is the size of the observable universe, the universe we observe today. And there's nothing that says the whole universe back here would just be the observed universe. What sets the size of the universe back here? Well, if there was more universe here, that would expand and we would never see it. And so inflation may imply that there's a vast universe beyond the universe that we can see today. And some back-of-the-envelope calculations would say that the size of the full universe might be 10 to the 60 more than our observable universe in volume. So the universe that you can see is maybe only a small fraction of the total. Well, just to put this into perspective, if you want to do some cosmology in your kitchen tonight, this is the analogy for how inflation works. So as I said, inflation takes quantum fluctuations and blows them up to scales that makes galaxies, blah, blah, blah. Well, the analogy in hardware that you can enjoy at home is a resistor. It has noise on it. It has thermal noise, which is ultimately associated with quantum mechanics. And with a good amplifier, I can take the noise on that resistor and I can amplify it, and I can put that output into a speaker, and I hear a hiss. And that hiss is quantum mechanical noise, right? But it's been blown up, so you can hear it. We would love to observe this, but we observe the microwave background. So there's one more step in the process. You have to take this speaker and shake a bowl of Jell-O with it, okay? And the analogy with the microwave background is this surface is a plasma. I mentioned it's ionized, it's glowing, and you're going to shake it and then observe the surface of the Jell-O or the plasma if you're a cosmologist. And so that's basically a description of what we do. We observe the surface of the Jell-O and try and infer properties of, well, we can actually say a lot about the Jell-O, first of all, and that's interesting. But we can also perhaps work backwards and infer properties of the amplification process, which is inflation. Okay, so here's our current state-of-the-art best all-time image of the microwave background. And what I've done here is I've taken off that big constant term. So now we're just looking at the variations, minute variations in the microwave background. And with the right set of eyes, you can see that the structures here, there are some hints that are consistent with inflation just by looking at this picture. So remember I said the horizon size, the causal patch, is about a degree across. But there are clearly structures here that are much bigger than that. So those structures had to have been set up by something like inflation, because they're coherent across such large scales. Light wouldn't have traveled far enough to set these sorts of things up. So that just basic view is already telling you something about inflation. You can also perhaps see there's kind of a characteristic bumpiness associated with this map. And that bump is associated with the Jell-O physics. And I'll say a little bit about that. So about 2001, there was a balloon experiment called Boomerang. This is before the map I showed you. And Boomerang zoomed in on a small patch of sky. And back then, we were studying the temperature, these bumps. And this is a smaller patch, about 25 degrees across. And you can see there's kind of a characteristic size to these bumps. And that characteristic size has to do with the Jell-O. There's a speed of sound in the Jell-O, and there's a speed of sound in the plasma of the microwave background. The time of inflation was 380,000 years ago, so you can kind of work out that the first thing that could collapse would be about 380,000 years times the speed of sound. That would be the size of the biggest structure. And it turns out the speed of sound is about a third in the plasma. And so you can calculate quite precisely how big these lumps should be. But we view these lumps through the entire universe. Okay, so if the universe is curved, it acts as a lens, and we see these bumps spread out. So what we see here, this is data from Boomerang. This is a calculation of what the bumps should look like if we lived in a universe that was flat. This is a calculation of what the bumps should look like if we lived in a positively curved universe. They get blown up. And here's the case of a negatively curved universe. And just by eye, you can see that the size of the bumps are consistent with a flat universe. And that's exactly what inflation predicts, because we don't know the initial shape of the universe. Maybe it was a donut before inflation. But because whatever the original geometry was, it gets blown up by such a large factor, locally it's going to look pretty flat. It's like we're standing here on the Earth. We might not know it's curved because it locally is going to look flat because it's so big. Same idea. So that's a prediction of inflation. And here you go. You can just see by eye that that's basically correct. So the map I showed, we can turn this into what I'll call a sonogram. But basically what this is telling us is, rather than just look at structures in the map, we can mathematically describe how much variation is in the map at each angular scale in the map. So the y-axis here is the amount of variation I see in the map. And the x-axis here is the angular scale. It's written as angular frequency, which means large structures, like 10 degrees here on the left, have low angular frequency. And small structures, 0.1 degrees and finer, have high angular frequency. So large structures are over here on the left, and small structures are over here on the right. Now what you see are data on the temperature variations, okay? Notice the log scale here. So this is over quite a wide range, and the black line is a fit to the data. And the fit is remarkably good. The two lines here you see are describe the theoretical uncertainty in the fit. So first thing we see is this big peak here. That's the largest scale, as I said, in the jello, the one that Boomerang saw. But there are smaller structures too. The jello kind of responds to variations. And so there's this whole acoustic series of peaks. And the data are so good now, you see 1, 2, 3, 4, 5, 6, 7, 8, 9 peaks. Really quite a lot of progress on the experimental end. And this is telling us about the jello, and it's telling us about the state of the universe with incredible precision. Based on this measurement and supporting measurements, we know that the universe contains dark energy, dark matter, and the matter we are associated with, baryonic matter, is just a small fraction. And furthermore, we know their proportions to better than 1%, okay? So very, very precise. We know the age of the universe, 13.8 billion years, and we know that number now to better than 0.2%. We can see the effects even of things like the generation of first stars way after the Big Bang. That produces a detectable effect in this data, and we know about that. So that's impressive, but also the spectrum here has all the fingerprints of inflation. So first of all, I mentioned this peak, the size of this peak. That's exactly consistent with the universe being flat to better than 1%. Now, at the very large scales, as I said, those are scales where the jello hasn't had time to react, okay? It's scales that are bigger than the sound speed times the age of the universe in the jello. These kinds of structures out here are really set up by inflation. You're looking at the initial spectrum from inflation out here. And so, as I mentioned, there are structures out here that are larger than that horizon size, that 1 degree, and that's a prediction of inflation. Furthermore, you can see that this spectrum out here looks pretty flat, but is not quite flat. And that is another prediction of inflation. This is basically saying that the noise that comes out of the resistor, when you stretch it so much, it goes to a particular shape, a particular spectrum. It's kind of like taking the square root of a positive number. If you start out with 2 and take the square root 60 times, you eventually get something pretty close to 1. It's kind of the same idea. And so inflation predicts this to be flat, but not quite, because inflation stops. This is supposed to tilt slightly red, and bingo, that's exactly what we see. And finally, inflation had a beginning. It set these quantum fluctuations, the vibrations, all started at a particular time. And that produces a particular phasing of these peaks. And the phasing of the peaks we see here are all consistent with that picture. And once again, that's another prediction of inflation. So while you might be skeptical about if inflation is the correct theory or what the basis of it is, I mean, there's no doubt that in the past couple decades, experimentally, it really fits the data. So what else could we do to study the properties of inflation? The microwave background here really prevents us from seeing back to these early times. We've got some clues that I mentioned. And so there's an interesting thing. I said that inflation takes quantum fluctuations and makes these density waves, which turn into large-scale structure in galaxies and so forth. But it's also possible, if there's a connection between quantum mechanics and gravity, that there would be quantum gravitational fluctuations, and inflation would expand those to make a background of gravitational waves. And rather than the previous tests I mentioned, which test whether inflation is right or not, this is really testing how inflation works. So some models of inflation produce a lot of gravitational waves. Some models of inflation don't produce so much. So we're kind of doing a second order test here. If we look for gravitational waves, we can say something about actually more about the process of inflation rather than just its bare existence. Now, so well, great. So how do we detect that? Well, these gravitational waves would be with us today, and it might be possible, perhaps, to detect them directly. But it's really hard. I mean, we're having trouble detecting fairly bright gravitational waves in the nearby universe. So diffuse background like this is a real challenge, though not impossible. Those gravitational waves also, though, stretch and squeeze space as they travel. The arrows show as a wave's traveling, it stretches and squeezes space. And that stretching and squeezing can produce a signature in the microwave background that's best detected by these polarization features. So that's the signal that we've been spending the last 15 years of our lives working on. But by the way, these gravitational waves, if they're with us today, they actually go all the way back to the period of inflation. They don't interact really with the rest of the universe. So one day in the distant future, perhaps, we could look back at this epoch more directly. Okay, so the secret signal here, as I mentioned, was to look for a polarization pattern. Now, polarization, you might be familiar, like if you look at the surface of a lake with the sun shining on it, the light coming off the lake scatters off the lake, and it's polarized. It's why people wear polarized sunglasses. And the microwave background is strongly scattered, as I said, by electrons. Okay, so we've got scattering. Good, so we should have some polarization. However, this analogy with the lake, part of the reason it looks polarized is because the whole sky isn't glowing with the temperature of the sun, thank goodness. And so if the whole sky were glowing, that would basically cancel out the net effect. So you need scattering, but you also need some temperature or light difference to produce a net effect. In the microwave background here, here's our electron. It's bathed in a bath of radiation. And that radiation is pretty uniform. So yeah, it's going to produce a polarization, but it's only going to scatter the tiny temperature difference it sees. So it's much fainter than the temperature variations. Now this is what I'm showing here is a density wave. And as this density wave is traveling along, it's got regions where the plasma is squeezed and it's hotter, and it's got regions where it's rarefied and cooler. And so if I'm an electron sitting here, if I look in the forward and back directions, I see, in this case, a cooler temperature, and if I look out to the sides, I see a hotter temperature. So there's a net difference, and I can scatter that as an electron, and I can make a small polarization signal. Well, what about gravitational waves? Gravitational waves, as they travel, they stretch space in one direction and they squeeze it in the other direction. And that's a little bit different than a density wave like this. The stretching and squeezing creates a temperature difference, but there's a different effect. It's a bit subtle, but you can understand that a density wave like this, it's just a compression wave. It's like a sound wave. It doesn't have a handedness. It doesn't know its left from its right. A gravitational wave actually does. It does know its handedness because gravitational waves are like a little bit like light waves. They come in two polarizations. So you can have right-hand polarized light wave. Gravitational wave is polarized. It knows its right from its left. So there is a distinct difference here. And so here's the idea. We measure a polarization pattern on the sky, and we look for a part of the pattern that changes sign when we put it in a mirror, okay? And so there's two kinds of polarization pattern. One is called an E-mode pattern, shown by these lines up here. This is a polarization pattern. If I put it in the mirror, it isn't affected. These kind of pinwheely patterns are called a B-mode pattern, and they have the property that if I put it in a mirror, the pinwheel changes sign. And here's the key point. A density wave doesn't know its right from its left. It can't produce these kinds of pinwheel patterns. It can only make an E-mode pattern. A gravitational wave can do both. So if we see something that has this B-mode characteristic, it can't have been made by a density wave, and it may be a signature of a gravitational wave. Okay, well, this is not easy. Again, here's the sonogram I showed with the temperature variations. And now let's go look at what's been done in polarization. Polarization was discovered in the early 2000s, detected. And today, here's the state of measurements. You can see they're noisier than the temperature measurements. But considering where we were in 2000, this is pretty darn good progress. And these acoustic bumps, as you see, are related to the bumps in the jello that we see in the temperature anisotropies. There's a particular phasing, the polarizations associated with the flowing of matter into denser regions. What I think is most impressive is the line you see here that's going through all these points is not a fit. It's based on basically the temperature fit. And so you measure the temperature and you predict what the polarization is going to be, and boom, you see all the peaks. But that's not the signal we want to see. It's also a lot fainter. You can see here on these units, it's about 1% of the very faint temperature signal. The signal we want to see is B modes, and those have been detected just this year. Here are some detections here on finer angular scales, not very good in comparison to the E modes, and certainly got nothing on the temperature data. But here's a B mode polarization pattern. Unfortunately, that's also not the signal we want. This signal is something else. It's called gravitational lensing. And so what this is from is an effect where the microwave background travels to us through the rest of the universe. And the rest of the universe has got structure in it. It's got matter, and that matter perturbs the path of the photons. It bends them slightly through a gravitational effect. Einstein's equations predict gravitational lensing. This is basically what's happening here. So the pattern from the microwave background gets slightly distorted. And so if I flip back and forth, you can see the effect. It's not big, but it's definitely there. And it does the same thing in polarization. It takes the background E-mode pattern and slightly distorts it, and that turns it into a little bit of a B-mode pattern. So the signal we're seeing here, here is that pattern, this lensing pattern. Well, that's pretty cool. I mean, it'll tell you stuff about the formation of structure, but it's not telling us about inflation. The signal we're actually after is down here. Okay, all the way at the bottom. And that is a big signal. This is at an amplitude. So that's the gravitational wave signal. Its amplitude is characterized by a number called R. So this is an R of about 10%. It's kind of the maximum possible signal these days. And we want to look for a signal at about that level or maybe 10 times fainter. Now, the exciting thing is that at this level, we're actually now testing new properties of inflation. This territory is unexplored, and the simplest models of inflation, well, I have to be careful. The first models of inflation, and I would say perhaps the simplest, they would predict a signal in this range. Now, there are other models of inflation where it would say, it could be all the way off the bottom of the chart. But this is the regime we're in. And in the next few years, we're going to be pushing in right around in here. And so that's really quite interesting. Some have likened this to the search for a wild goose. And that is your wild goose. OK, so about 2000, we decided to build the perfect instrument to detect this polarization signal, this wild goose. And well, I guess one thing you can see if I go back to this chart without the goose, the signal here peaks at a pretty large scale. If you look up here, it's about 2 degrees on the sky. That's pretty big. The problem isn't the size that's big, The problem is it's extremely faint. So the main challenge for us is to build a system that can get an incredible sensitivity to detect this very faint signal. And so what we realized is in order to do that, we don't need a big telescope. A big telescope gives us angular resolution. We can do this with a small telescope. And I love small telescopes. But we do need to collect a lot of light. It has to collect, has to have a huge field of view. And ta-da, a simple refracting telescope can do that. So this design, which is a rather modest affair, it's a 26 centimeter telescope, has a 20-degree field of view, and so it's got an enormous focal plane of detectors, which means it's very sensitive. And once you've embraced the idea of a small telescope, this is just great. We can take our whole telescope and we can cool it down to 4 degrees, which means we don't have to worry about emitting photons. Try to do that with your 10-meter telescope. We can rotate the whole telescope around, so if there's any polarization associated with the telescope, it's going to come out, because we can easily spin it around. And all this stuff here is absorbing, so we don't have to worry about light going out to strange angles and seeing the Earth or other things. It's absorbed here on the walls of the instrument, and which are cooled to 4 Kelvin, so that's really nice. And Brian and myself came up with this idea over a game of tennis. And then the second part of our program was to build this in phases. So we were very excited about the small telescope. We wanted to test it with conventional detectors that we had at the time. And it got out into the field in about 2006. And then we've been building up progressively more sensitivity, more power. And this has really been intimately connected with the detector technology. Our second phase of the experiment, called Bicep 2, is 10 times faster. We make a measurement in 10 times less time than Bicep 1. And the Keck array is 5 times faster than Bicep 2. So over the years, we've gotten about a factor of 50 in how fast we can make the measurements. The key technology we use is a detector called a bolometer. Bolometer detects heat. This is an early example of a bolometer system. In fact, this was a superconducting bolometer, believe it or not, back in 1946. And in spite of a certain gift of marketing, they didn't really catch on in astronomy until about the 60s. And the way a bolometer works is light is absorbed by an absorber, something that just turns the light into heat. And we measure the temperature of the absorber. And so the power from the light causes the absorber to rise up. We put a sensitive thermometer on the absorber, which is isolated, and we can infer how much light was incident on our detector. Now, it's not quite so easy. One of the things is you have to worry about the fact that there's thermal noise in the system, so we have to cool these detectors down to low temperatures to get rid of the thermal noise, a couple tenths of a degree above absolute zero. This is a modern, well, not so modern, more modern bolometer, and the absorber here is this kind of spiderwebby structure. It's got an absorbing film that catches the radiation, which is bigger than the spacing in the mesh. But all the material heat capacity from the detector is gone because I've eaten it all away. This is a freestanding structure, and there's very little material left. And then the spider here at the center is the thermometer that measures the power. So this was a state-of-the-art detector circa 2000, and they're quite good. They're very sensitive. About this time, the detectors had gotten to the point where their sensitivity was so good that they're limited by noise from the microwave background itself. There's kind of a noise associated with photons in the background, and that's a fundamental limit. This detector reaches that limit. And so if you want to build a more sensitive instrument, you can't build a more sensitive detector. You have to build a lot more detectors. Even before Bicep, we came up, well, Jonas Zmiedzinis came up with a rather revolutionary idea for how to do such a thing. And the idea is to use superconductivity and to manipulate the electromagnetic field to basically make a custom polarimeter. And this is a very futuristic idea at the time, very artsy, I guess, very sketchy. But the idea is that we could extract multiple colors out of our camera and get all the information out, and it would be great. And we could build, instead of these individual detectors, we could build like real, true polarimeters. And this structure isn't just a detector. It guides the radiation. It chooses the spectral band that we observe with a filter. And finally, it detects polarization and detects the radiation at the very end with a detector. So it's more than just a detector. It's kind of like a printed polarization-sensitive camera. And the cool thing is you can build this structure in a microlab, and you can mass produce the detector arrays. And so that's what we did. Now, the futuristic structure I showed you, we haven't actually quite achieved that. The arrays we have here are only working in a single color, but this is the old technology in Bicep 1 with discrete detectors and feeds that collimate the light. And the new technology here puts all of that onto a single piece of silicon. And in fact, that single piece of silicon's got about twice the power of the whole focal plane you see here. And the people who make these at the Microlab, this is Tony Turner, our heroes. The Microlab at JPL is really a fab used to make like computer chips in industry, but it's designed for research, for custom things that NASA wants to do. And we would be nowhere without such a wonderful facility. So here's what the new detector arrays look like compared to the old ones. And the fact that there are many more detectors and actually that they work a little better gives us overall about a factor of 10. The other part of our program is a team of dedicated scientists. We're working here with people who've basically decided to put a decade of their lives into this pursuit of inflationary polarization to understand about the early universe. And I think that's pretty remarkable. I mean, when push comes to shove, there aren't many people who are willing to do that. And I think you can see that many of the people here are young. So our team is based on, I didn't circle myself, graduate students, and these graduate students play leading roles in our experiment, and in some cases have invented things that make the experiment possible. And similarly, postdocs. And so the efforts of those young scientists is really what makes our program work. Because we observe in the microwave, millimeter wave, we want to go to a site on Earth that is very good for these observations. Millimeter waves are strongly absorbed by water vapor, so we want to go to a very dry site. And the world's best site for these observations is the South Pole. And that's because the air is remarkably dry. And part of the reason it's dry is because it's so cold. But it has some other features. One feature you can see here, this is the airstrip. There's a huge amount of facilities that have been brought in. The US has had a continuous presence at the South Pole for more than 50 years. And over those 50 years, there's a lot of logistical support. In the winter, the sun goes down for 6 months and it never comes back up. And that's good for astronomy because the diurnal variations that stir up turbulence in the atmosphere don't happen at the South Pole. And finally, it's pretty high. The altitude of the South Pole is about 10,000 feet. Most of that is solid ice. This shows how our observations are done. We call it relentless observing. And that's because the other feature at the South Pole is that any patch of sky just goes around in a circle. So we can observe it 24 hours a day, 7 days a week, not 365 days a year, but every day during the winter. And so that's what we do day after day, week after week, year after year. We scan our telescope across the sky, and we build up integration time, because the main challenge here is to get sensitivity. And in this time lapse, obviously this is during the winter, you can see the plane of the galaxy here rotating overhead, and we're scanning the telescope back and forth. And you can see some satellites that cross at the polar satellites. And yeah, those are the aurora. And so we do this every day, and eventually we get to the point where we have a high quality map. So this is the map that we produced last year from the Bicep 2 experiment as our polarization pattern. And if you're expert enough, you can tell by eye that it's mostly E modes, which is to say the pattern doesn't change very much if I put it in a mirror. Mathematically, I can extract the B mode component from this map, and here it is. It's quite small. I can blow that up and colorize it according to the way the pinwheels are rotating. And this is actually pretty cool, because it may not look it, but these structures here are detected. Any individual structure you see, I mean, this map's got noise in it, but the overall pattern we see with a lot of statistical significance. It's more than 5 sigma. So then the question is what is it? Well, we have to be careful. The galaxy also is polarized, and because our initial measurements are all at one frequency, we have to be careful about the polarization from the galaxy. And the polarization of the galaxy has to do with the magnetic field of the galaxy, and there's no reason it can't have a B mode component. There are 2 flavors the galaxy emits in. There's a very kind of red component called synchrotron, which is spiraling electrons, and here's a map of synchrotron polarized emission. And then there's a blue component, which is dust grains, which are aligned with the magnetic field. And this map is different. This map is not polarized. It's based on intensity. And so at the time that we came out with these measurements last year, we had data for synchrotron, and we could show that it was negligible. For dust, there was no polarized map. And so we had to extrapolate based on models, which are based on this intensity picture. We don't know the polarization. And it looked like the synchrotron's completely negligible, and the dust is small. I mean, it's not, according to the models, not big. And most people who studied the dust would agree with those models at the time. However, we really wanted to see if we could do better. And the Planck Satellite, this is a European satellite that made that beautiful map. It's flying detectors developed at JPL, these spiderwebs, and it maps the sky in multiple bands. And so at the time, the Planck Satellite had the best data on what the polarized galaxy looked like. And here are the maps in temperature. So this is really great. Here's 9 bands. The blue stuff you see here is the microwave background variations, and the red splotch across the middle is the galaxy. And as I go to low frequencies here, I see the galaxy in synchrotron, and the synchrotron goes down, down, and then coming back up here, that's dust emission. By the time I get to these high frequency bands, the dust is just overwhelmingly bright. So I can use this, and because of the importance of this topic, our teams decided to collaborate before this map in polarization was available to see what we could say about the galaxy. 7 of these maps are available in polarization, and this was the best data available. And this is what the galaxy looks like in polarization. The brightness here is the intensity, and the brush strokes are the direction of the magnetic field from the polarization. And it looks pretty awesome. Now, what we learned from this was that, first of all, the galaxy is the dust is a bit more polarized than what the models said. But more importantly, there's a lot of variation in the polarization. So any region, the amount of polarization is variable. And so you really need to take the data, which is what we wanted to do from the beginning, and do a comparison. There is an aspect of this map which is less wonderful. If I take the small region of sky that we deeply observed and look at the signal there, this is what the polarized signal looks like. I can ask what the noise looks like, and the noise and the signal are pretty similar. So in small regions of the sky, the map's kind of noisy. And so the other thing we wanted to do was bring in new data. So in the last year, we've now got even better data from the Keck array, that thing with the 5 receivers. So this is the original map. Now this is not in B modes, this is in E modes. So this is a brighter signal. But I think you get a good visual representation here for the quality of the data. Okay, so this is the E mode map. Bigger signal, not a super bright signal, but this is the E mode map made with Bicep 2. And then here's the new completely independent E mode map made with the Keck array. So very, very, very similar. And here's the combination. So that is now the best data. And finally, we took that polarization map and we asked, is there a B mode signal detected? So this is the signal we see from Bicep 2 before we do any subtraction of the galaxy. And as I mentioned, this is the amplitude of the gravitational wave signal measured by this number R. And the total signal here is big. But this is the total signal on the sky, not the signal from the microwave background necessarily. We have to subtract the foregrounds. Okay, well first let's look at what the new data look like from Bicep 2 and Keck. And they're very similar. And the error bars have gotten smaller. Okay, so we really have a high signal to noise detection of this pattern on the sky. Now we had to take Planck to remove the dust. Okay, so here's the estimate of the dust. And the dust is significant. It's bigger than what the models predicted. Also, importantly, the error bars are big, or unfortunately. And really, this is driven by the noise that's in the Planck data. And now I can subtract the dust from the total and say, do we see a gravitational wave signal? Well, here's the answer. Here's where we are today. This is the best fit amplitude with the error bars. And so you might say, well, you know, there's something positive here. And it's true that the data don't favor zero gravitational wave signal. But the error bars are too big to say that the signal couldn't all be explained by dust. And here's the 1 sigma size of the errors, here's the 2 sigma size. So an all dust case, or no gravitational wave signal, is about 1.5 sigma, which is not strong enough to say that it can't all be dust. But yet, intriguingly, there seems to be a positive signal. So as I said, this is a hunt in progress. Okay, so just quickly, some of the steps we're making to narrow down the hunt. An experiment called Spider recently flew, just in January, actually on January 1st. It's like Boomerang. It goes around Antarctica with the polar winds. Didn't quite make it all the way around. Here's where it ended up. And it's got 2 colors and 6 focal planes. And we just have the data now, but it looks great. Here's a picture from Spider on a GoPro. This is near the edge of space at about 120,000 feet. Here's Ross Island in Antarctica, the Ross Ice Shelf. And don't worry, the Earth hasn't shrunk. This is an effect of the fisheye lens on the camera. We've been hard at work at the South Pole, putting in new receivers. The first step is to add colors. So the detector arrays we've developed, it's quite straightforward to scale them up to higher and lower frequencies, and so we're doing that. 4 of the 5 Keck receivers are now operating at different frequencies, 2 of them at this higher frequency band. This is just to show that I occasionally do get in the lab. We have a new instrument called Bicep 3. We call it a super receiver because it collects as much light as 10 Keck receivers in one telescope, one huge, not so huge, 55 centimeter telescope. And it's all operating at a different frequency, actually at 95 gigahertz. And so when it's fully going, it'll have the same sensitivity as all of Keck, and we will rapidly catch up in another band, which is critical to see how much foreground is in the total signal. Here's just a picture of the instrument going up into the telescope mount. It goes up on these rails, and this guy is kind of a ham, so you can see him hard at work here and then not so hard at work playing with a yo-yo. But this process of lifting the receiver up kind of takes a day. But once that's completed, we started to get our first data from the sky. And now the receiver's operating during the winter. So there's one person who's operating it during the Antarctic winter, and we're making progress. So thank you very much. My conclusions are that gravitational waves are very interesting. They can tell us about what powered inflation, what the process is. Inflation is going to tell us something about new physics. We need a new process to cause it to happen. It's got deep connections between quantum mechanics and gravity. It probably happens at energy scales associated with grand unification. I mean, it's really exciting. And the test here that we're after of gravitational waves is that only some models of inflation make copious gravitational waves. So we can test between models. The fact that we can reach back to this very early time, I think, is really quite amazing. Our current state of analysis with Planck is we do not falsify the all-dust model, but we do see a positive bias. And really, we're limited by our errors right now. New data is coming. It's on the way. Spider, Keck, and Bicep 3 are all making great progress. And look forward to the noise going down in stages, even this year. And stay tuned. Thank you.